Hello, Djordje Romanic here. Welcome to Fundamentals of Weather and Climate. We learned in a previous video that moist air is less dense than dry air. And that might sound counterintuitive, because how is it that adding moisture decreases the weight and density of something, of air? But that's what happens in the atmosphere. So please check that video to understand why that is happening. So if I have two same volumes of air, two volumes of air that are exactly the same, but one is moist, another one is dry. So this one has temperature of dry air equals, let's say, 20 degrees Celsius. And this one has temperature of this moist air also 20 degrees Celsius. So you would say nothing interesting, because two parcels of air of the same size, same temperature. But this one is dry, this one is moist. And let's say that moisture, namely water vapor molecules, are indicated with these red dots. Well, this one will have density ρd, this one will have density ρ of moist air. If the temperatures are the same, but this one is moist and this one is dry, are densities going to be the same? Well, I just told you, no. In fact, density of dry air will be larger than density of moist air. And I have entire video describing that. So in this video, I want to discuss how can we make these densities the same. There are two options. Of course, option number one is either remove moisture, remove water vapor from this parcel of air and densities will be the same, or add water vapor to this dry parcel of air for 1, 2, 3, 4, 5, 6, 7, 8 conceptual water vapor molecules, and you will make densities the same. But that's not interesting, that's trivial. Another way we can make densities the same is if we change temperature of the dry parcel of air. Namely, if the temperature of this dry parcel of air increases, that means that the density of this dry parcel of air will decrease. You know that from the concept of temperature that I discussed in great detail in my previous videos, in a number of videos. Because what is temperature? Well, temperature is jiggling of particles, molecules and atoms that are making substance, in this case air. When we increase temperature, jiggling increases, which means the average distance between particles increases, which means density decreases. Well, okay, so if I increase temperature of this parcel of air, density will decrease. So logical question is, how much I need to increase temperature so that density of this dry parcel of air actually decreases to the point it matches density of the moist parcel of air? And the answer is, you have to increase this temperature until temperature reaches virtual temperature. TV, we use this symbol. When temperature of this parcel of air reaches virtual temperature, then the density of this dry air will be the same as density of this moist air. So that's the concept of virtual temperature. Why does it matter? Who cares, you might say? Well, I'll give you one simple example why it matters. Imagine over here is the surface of the Earth, and this is height. We use Z to indicate height in this course. And imagine, conceptually, imagine that what we have is one parcel of air. I will indicate it as a square, so to speak. We have this parcel of air moving in this direction. It has temperature T, and it is moist. And there is another parcel of air of the same size, imagine these are the same sizes, also has temperature T, same temperatures, but this one is dry. Or you could say less moist than this moist one. And this parcel of air is moving in this direction. So clearly they will collide. When they collide, what will happen? Well, I just told you that the density of moist air is smaller than the density of dry air. So what will happen when they collide? We will have dry air close to the surface and moist air above it. So this one with moisture will end up above dry parcel of air. You might say, how is this associated with the concept of virtual temperature? Well, it is associated with the concept of virtual temperature because this moist air will have certain value of virtual temperature, whereas the dry air has virtual temperature that is equal to actual temperature. So that means that virtual temperature of this moist air is larger than this temperature of the dry air. And because this temperature is larger, this parcel of air, this virtual temperature is larger than this temperature. This parcel of air will behave as it is warmer than this dry air. It is not warmer. The temperatures are the same, but it has moisture in the amount that this virtual temperature is larger than this temperature, and it will be warmer. And we know from the principle of buoyancy that warm air will go above cold air. Well, here these two air masses are of the same temperature, but this one is moist, so it will behave as it is warmer, and it will situate itself above dry air. And clearly, this is very important in atmospheric dynamics and thermodynamics and formation of clouds, because if you have two air masses at the same temperature, they collide, the moist one will go above dry one, and if there is a lot of moisture, you might have formation of a cloud. Perhaps it is even better to demonstrate this if I tell you what is the equation for virtual temperature. Because this is fundamental playlist, you know I'm not deriving equations here. I do that in advanced playlists. So I will just state the equation that virtual temperature is equal actual temperature 1 plus 0.61 times R. What is R? R is mixing ratio that we discussed in one of my previous videos. That is mass of water vapor divided by mass of dry air. And we express it in the units of grams per kilogram, despite the fact it is unitless. And you also know that in our atmosphere, the values are typically between close to 0 to maximum 18, 19 grams per kilogram. So you can see from this equation, if R is equal to 0, if the parcel of air is perfectly dry, then temperature is equal virtual temperature. And that's what I told you here. When the parcel of air is perfectly dry, is air ever perfectly dry in the atmosphere? Not really, but we can use it in this concept as it is. So if the air is dry, temperature is virtual temperature. So let's assume that this moist air had temperature of 20 degrees Celsius. So that means this temperature is 20 degrees Celsius, and this temperature is also 20 degrees Celsius. But this moist air had mixing ratio of, let's say, 15 grams per kilogram. So that's close to 18, so that's quite moist parcel of air. Now convert this to degrees Celsius. Convert this to kelvins. 15 grams per kilogram is 0.015 in the unitless case, in the unitless format. Plug in here and you will get that virtual temperature for this parcel of air is 23 degrees Celsius. So TV is equal 23 degrees Celsius. Here TV is equal T, because it's dry, equals 20 degrees Celsius. So now it's even clearer, because you have that two air masses of the same temperature, 20 degrees Celsius, collide. the moist one behaves as if temperature was 23 degrees Celsius, namely as the temperature was the virtual temperature, and therefore the moist air will situate itself above dry air. So to conclude, of course, what is the formal definition, therefore, of virtual temperature? Virtual temperature is the temperature that dry air would need to have in order to achieve the same density as moist air. And because dry air is heavier than moist air, then virtual temperature is always larger or equal than the actual temperature. And here is the equation without deriving it. So very, very useful concept to account for the amount of water vapor in a parcel of air, and we will use it a lot throughout this playlist on the fundamentals of weather and climate. Please make sure to like and subscribe and comment. It helps channel a lot. And until next lecture, goodbye.